Hello everybody, thank you for joining me again. This is part 2 of the Marconi 6200A 10MHz to 20GHz microwave radio test set, or MTS as it's commonly known. We have from part 1 moved on from resoldering the connectors and plugs that I demonstrated in the synthesizer module and also on the logic board. Now we've moved into the microwave chassis, which comes out of the main radio test set, and it's mounted in this section. It's quite easy to remove and it comes out as a complete unit. This particular test set has the step attenuator module, which is the same as what you find in other radio communication test sets from Marconi's product range. Not all test sets are fitted with this. This is an option, so I've disconnected this because the bit we're wanting to look at as far as the repair is concerned is beneath, and it's the RF path for the attenuator. Okay, just to explain, we have 3 yigs, all covering different frequency ranges of the test instrument, and then down here, I'll just shine the light in a better position, we have a pin switch here, which, as you can see if it focuses a bit better, we have an input from this yig here, which is a 2 to 8 GHz input. Then we have a 8 to 12 GHz input and a 12 to 20 GHz input. And then from the synthesizer unit, which is what I showed in the first video, the synthesizer connects here on this SMA connector, and that gives us a 10 MHz to 2 GHz input, as can be seen there. So basically what happens is the test set selects the different signal sources, the yigs, through these pins. There's some selector pins here, you can just see. There's 5 in total, because I think one of them's a supply and the other will be a ground connection probably, or the other way around, to enable them. And then obviously whichever signal's been selected from this pin switch gets passed out in the RF output to this coupler, and then what happens is then it goes into this, what is I believe to be a pin diode attenuator. And I've read the manual, the instruction manual that I have for the test set also has a service section in the back, which most of these manuals don't have. But it's a functional description and a block diagram of the pin diode and all this RF microwave assembly. It gives you an overall block diagram, but it doesn't mention this as a pin diode attenuator. It mentions this as a pick-off, some kind of capacitive pick-off that then feeds a signal back into the limiter circuit. But what it doesn't do is explain in the functional description of how the limiter works. Now, as far as I'm aware, and the knowledge I have on yigs, you can't, reduce the RF output power and increase the RF output power. I've got some documents on yigs which I've read quite extensively, and they don't indicate that the yig output power is controllable from the yig itself. So it's unlikely that there's some kind of ALC voltage that's controlling the yigs and the synthesizer in order to produce a calibrated level output. It's got to be done through the pulse modulator. This is a pulse modulator here that modulates the RF carrier, and then this is some kind of a pin diode modulator or attenuator, or acts as an attenuator. So, and there's a signal coax here which I measured a voltage on when I talked about in my previous video, part 1, about what that voltage is. Now it suddenly changes, because as you adjust the RF level up and down, the voltage to that should change very gradually up and down as well, proportional to what level of RF should be passing through. And in this case, this voltage is suddenly changing on one digital analog control value from say 3 volts to suddenly 0.6. It just shifts like that. The actual range is something from, I think it's 3 or 4 volts plus to 0 to minus 3 or 4 volts. So it goes throughout an entire swing. but this suddenly changes the voltage to it. So whether it's because the signal that it's sampling is meant to go back, which is this bin here, this is a sampler that's fed back to the synthesizer. What this does, the frequency counter connection, which is this, the frequency counter input comes in here and it mixes with the signal that's being fed on this directional coupler, and that produces an IF which is fed out on this SMA to the synthesizer, and that's how it gets its frequency counter function up to 20 gigahertz. But the actual signal path leaving goes through this coupler, and a bit sampled off to this obviously to allow the frequency counter section to work, hits this diode attenuator, or attenuator, variable attenuator, and then goes to the step attenuator before it goes on the RF output, which is here. So this here I think is a pulse modulator. When the test set was working when it was fully assembled and I was testing the RF level output, I disconnected this from the synthesizer board that controls it on this connector, and it didn't make any difference anyway, so it's not like it's getting a voltage fed in this way which is influencing how that works insofar as attenuation is concerned of the RF signal. So what I'm going to do now, I'm going to do some experiments. I'm going to, now that I've removed the step attenuator module, which works because I've tested this independently and it does go through the 10, 20 and 40 dB ranges as well, so there's nothing wrong with that. I shall disconnect this SMA and this SMA, remove this coupler, and I feed a signal in here and take the output to a scalar detector, and we'll sweep from 10 megahertz to 20 gigahertz at 0 dBm going in and the scalar detector on the output, and we'll measure what happens, and we'll put a power supply on a very small current limit on this connection down there, which is where the signal's connected to, or the DC control voltage in this case is a little stud which solders there, and we will alter the voltage to see whether it influences the RF signal going through. And I might, if it doesn't work, then take it apart and see what it does. And what I shall also do as well, using this, what I think is a pulse modulator and what seems to be indicated in the diagram, I shall feed a signal from a signal generator, probably feed a square wave in at maybe 2 or 3 kilohertz, just to see what happens, to see if it modulates the amplitude of the carrier. So that's what we'll do next. I'll come back to you with that experiment in part 3. So thank you for watching. I shall come back in part 3 with further update.